Well, let me show you. Testing. Test. Test.
Amanda, could you please test the
Testing. Can you hear okay, Fred?
Test.
Okay, we'll go ahead and get started. Thank you all so much for coming tonight. We're very excited to have you. We have a fabulous talk and beautiful clear skies. I'm declaring it our bad luck with observing with bad weather is over. We just have clear skies from now on. So to stay tuned for after the talk for that. As always, we're going to start with trivia. I guess I'll introduce myself first. My name is Amanda. I'll be your MC. If you get emails, they're most likely from me, so I apologize if they're long and annoying, and I will say you're welcome if they are helpful. We'll start with trivia, then we'll go over the schedule for the rest of our talks this fall. Then you'll hear from Dr. Athira Menon about the fabulous lives of massive stars. We'll do Q&A and raffle, and then we will have stargazing. All right, our trivia. So how this happens, there are 5 questions. I'm going to show the question. You'll have time to think about it. Collaboration is strongly encouraged. Chat with folks around you. No Googling. And then I'll ask for answers. So you'll show me 1 if you think it's A, 2 for B, 3 for C, 4 for D. And we'll see what the consensus is in the room is. So our first question tonight. What do binary stars orbit? Oh, keep your answers to yourself for the moment. And we'll survey answers in a little bit. I'm not hearing much collaboration. No one is checking with their neighbors. All right, science only happens with collaboration. So thank you for chatting with folks around you. Let's see your answers. 3, 2, 1. Okay, I'm seeing a lot of 4s. I see a 1. I see a couple 1. And that is our answer. So it's actually like nothing. These stars are the largest number of stars observed in a single system. So our solar system, we have one. The sun makes it very easy to tell time. But what if we had more? So again, chat with folks around you. All right, let's vote. 3, 2, 1. Show me your answers. All right, I'm seeing a much bigger spread this time. Very fun. We've got some confident ones as well. The answer so far, I'll say, is 7. That doesn't mean there's not a more complicated system out there. The universe is infinitely big, but so far 7 is the most that's been observed. I imagine that would make telling time much more complicated by the sun. All right, question 3. Who discovered the first binary star system? All right, let's vote. 3, 2, 1. Let me see. I'm not seeing any Simon Cowells. All right, no one fell for that. Okay, wow, we can see some votes in the projector as well for William Herschel. So William Herschel is recorded as the first person, but there's actually evidence that the Doan civilization of the Mali Kingdom in Africa were the first to propose that a star named Sirius was a binary system. And this would have been absolutely incredible because with the technology of that time, there was no telescopes or magnifying power. So this was a very, very incredible discovery of ancient civilization. That's a great question. I think it's BC, 2000 BC maybe, very old. Herschel would have been the 1600s, 1700s, 1600s. Thank you. All right, question 4. Speaking of Sirius, Sirius is the brightest star in our night sky during the winter. It is also a binary star. What is the distance between the two stars? Astronomers love crazy units. So this is a crazy unit question. All right, I hate to cut any calculations short. I see people logicking their way through it, but let's go ahead and share your best guess. 3, 2, 1. All right, I'm seeing a wide variety of answers. I think I see all, but maybe I don't see 2.1 billion elephants, maybe. All right, but the answer, if you do the math, is 56.3 billion one trains. So if we say a one train is about half a mile, that's about 30 billion miles. So even though these stars have are related in gravity, they're still very far apart. Athira, do you want to correct my math on that? Okay. Just double checking. Not trying to lie to anybody here. Okay. All right. And our last question of the evening is, which of these objects can orbit a black hole? Wow, we're stunned to silence. All right, let's vote. 3, 2, 1. Okay, I'm seeing 4s, 5s, 2s. All right, well, here we love a trick question. It's all of these. Anything can orbit a black hole, it turns out. You might not want to, but you could, theoretically. All right, thank you so much for playing trivia with us. We love to check in on our prior knowledge. Yes, give yourself a round of applause. We love to check in with our prior knowledge before we learn new things, and I hope you all learn a lot today from Dr. We have a series in the spring as well. We just don't have dates for those yet. If you aren't on our mailing list, please send us an email to join. That's the best way to find out about our events. All right, and very shortly, you're going to hear from Dr. Athira Menon. She is a theoretical astrophysicist working as a postdoctoral fellow and lecturer here at Columbia University. She earns a living by constructing simulations and mathematical models of stars to understand how they light up our universe. Along with physics, she enjoys history, culture, and dancing. All right, take it away.
Can you hear me? Is it through my mic? Yes, it is. Okay, great. All right. I don't think we need to dwell on this. We can move on. Oh, hello there. He's here to learn about stars too. That's just great. Awesome. Okay. Can we dim the lights, please, a bit? So we're going to start our stargazing session from here. Let's go right away into that. Once the lights are dim. Yes, thank you. All right. Welcome to the night sky. This is a picture of a part of the autumn part of the Northern Hemisphere. I'm going to press a button and something's going to change on that screen. I want you to tell me if you know something different about one star. Did anyone see that? Let's try again. How about now? No? Okay, let me help you out. Notice a square. And now, did anyone see a star going bright and dim? Somewhere over there? Look again. The first ones to see that were, in fact, the Egyptians 3,200 years ago. right? And they made an almanac with it. They made a calendar of lucky and unlucky days with it. And the reason is because that star seems to brighten dim every 2.8 or 3 days overall. And they could see it with the naked eye. If you're good with your eyesight, you might be able to see it today as well, depending on what Algol was doing. So we all love our mythology, and you know how astronomers do this. They draw random shapes on the sky and then associate a story with it. That particular constellation where this star was dimming and brightening is called Perseus. Are you all familiar with this great Greek legend, right? The legend of Perseus. He goes on this rescue mission to save Andromeda, and on the way has to slay a monster called Medusa, whose gaze would turn you into stone if she caught you. So using Athena's mirror, he manages to evade her and finally slay her by cutting off her head. And that there is now called the demon star because it's the wink of Medusa. And this is how astronomers draw Perseus in the sky. Don't ask me the logic for this. I was born in a much later era before they drew these things out. But that's Medusa's winking eye right there. And now we know, much later after the Egyptians, this is not something to be worried about. This is, in fact, an eclipsing binary system. One star goes in front of the other every 2.8 or so days. So when the bigger star goes in front of the other one, you can see this dip in the brightness, yes? This eclipse is what is called the wink of Medusa. Now, we know it more popularly using the Arabic term. It's called al-Ghul in Arabic. Medusa winks at you every 2.8 days. That wink is long, by the way. It's not like our perfunctory wink. It lasts for about 10 hours. It's a long wink. Make sure you go back and wink right at her, okay? Okay, so next picture. This is now traveling to the southern hemisphere. Do you see two clouds there? They're not clouds, actually. Do you know what they are? Louder? Galaxies, yes. And what galaxies? No. Yes? The Magellanic Clouds. There you go. The large Magellanic Cloud and the small Magellanic Cloud. And do you know why they're called Magellanic Clouds? They're named after a famous explorer, Magellan. Because these guys are satellite galaxies of our own Milky Way. And just like the moon goes around the Earth, you have two cute little satellite galaxies going around the Milky Way as well. Welcome. Now, let's zoom into one part of the large Magellanic Cloud. This is what we call a stellar nursery, right? A nursery of young stars. And in here, you have a variety of young massive stars. Now, massive stars are not like our sun. Our sun is, I'm sorry to say, a bit boring in many ways, you know. For one thing, it's not massive. It's very small. These guys are at least 8 times heavier than our sun. And in that nursery over here, a region I study quite a lot myself, we have measured a star that goes up to 300 times the mass of our sun. Now, the interesting fact is, most massive stars live in binary systems. They don't live alone. Another reason why the sun is so boring, because it is single, it is solo. Yes, I know it's a very sentimental thing to have the sun rise and set, yes, but as an astronomer, massive stars are much more dramatic and dynamic as they go. So here you have 2 massive stars orbiting eclipses that Algol does as well. Eclipsing binaries like this exist in plenty. And we have other ways of detecting massive stars. When you look at the spectra, the colors move back and forth. You've got some colors going blue and then red, and they keep moving back and forth. So these are just some astronomy ways to understand whether a system is a binary system or not. Eclipses and the color change of the spectra. Now, binaries, companionship conversations, right? So just like we have our own companionships and our own problems, a lot about whether you will live and die with your companion depends on what kind of conversations you have. Some conversations don't tend to go too well, as you all are quite aware, I'm sure. And like I told you, massive stars tend to be dramatic. If a conversation's not going well, the other one will suck the mass right away from the other star. We call these, and I kid you not, vampire stars. They exist in plenty. In fact, Algol is also a vampire star too. One of them is. And so after this conversation, the two stars will eventually detach and live apart effectively as single people/stars and never interact with each other again. That didn't go quite well. On the other hand, some conversations go too well. This is a contact binary system, also a system I study a lot. In here, the conversation's gone so well that they're exchanging a long stellar kiss. It lasts for millions of years. We're talking about stars here, right? So in this case, the two stars have connected, they're exchanging mass, and we call these contact binaries. They're not very common, actually. They're quite on the rarer side as massive binaries come and go, but they're very interesting to study because when you do simulations that I'm involved in, these are 3D simulations, eventually the two stars will end up merging. The bigger star swallows the smaller star, which then falls in towards the center of the bigger star. As you can see here, that's the teeny tiny small star falling in. Eventually, that one will get completely absorbed and become one single star. A new star is born. So if you thought that stars just form from ashes and dust of previous generations of stars, well, that's not quite the case. You can get newborn stars this way as well, through the merging of two stars. But here's the catch. Unlike us, when we make babies, right, they go through the stages of infancy, they become toddlers, and they become adolescents, and then adults. When stars merge, they make middle-aged babies. They skip right away into the halfway stage of their lives. And so this is the main reason a rather newish field in the field of astronomy and astrophysics. So here, these stars are called blue supergiants. They're actually middle-aged stars, which means they're halfway through their lives, right? About to soon eventually become supernovae and black holes, which we'll get to in a moment. But what has happened to make these stars, which, by the way, are the brightest stars in any galaxy, you can see them out to many millions of parsecs. That's a fancy unit in astronomy, but that just means many, many millions of light years, right? They're so bright, you can see them in the optical as well. What has happened to make them is that a big star, a supergiant star, engulfed its companion just the way you saw that. And eventually they merged to lead to these blue supergiants. Now, for whatever reason, a lot of people picked up the news. They made it catastrophic. They quoted me without my knowledge. They wrote quips from my paper. Apparently, I said these things. I don't remember that. But okay, that's fine. You know, it is not incorrect what they wrote, but that's sometimes how science journalism works. You get to know things after they've happened. Okay, so we talked a lot about how stars live. Let's talk about how these massive stars die. Well, eventually these stars they're heavy, right? So when they run out of fuel in their centers, what is going to happen? They are going to eventually collapse. And they collapse so rapidly that the core of the star will bounce back, send out a shock wave, and then you get an explosion, a supernova. A supernova is the final end state of a massive star. Yeah? It is how most massive stars are going to die, most of them. And they're very important for us. Because if massive stars don't exist, and if these supernovae don't go off, you actually don't get new stars. You don't get new planets, no new solar systems, and certainly no life. All the carbon, nitrogen, oxygen, iron that's going into your body, that's gone to make you, that's made your DNA, was once churned inside the bowels of these massive stars. And only when they explode as supernovae can they be ripped apart and then scattered across the interstellar world. So supernovae are extremely important. They are roughly about 1,000,000 trillion times the energy released from the atomic bomb. That's just about so little, right? So if you're in the vicinity, it's going to be catastrophic for you. However, when we look for supernovae, this is what telescopes find. This should be relatively easier. Hopefully you're primed now to find it. Can you tell me where the supernova is going off? This galaxy is called the Pinwheel Galaxy, by the way. Do you guys see it? Right? So it's so bright. Can you imagine how bright it is for it to stand out against the background of this entire galaxy? It outshines its galaxy. And this lasts for about a few weeks to a few months, depending on Pinwheel Galaxy, which is a few trillion kilometers away. And so that means the light took a few trillion kilometers to reach us. That's how old that galaxy is. And that's how old that light is. That light reached us only in 2023, but it had traveled a few trillion kilometers to reach us. Now, sometimes the pictures are much prettier. I'm sorry for the graininess of the image, but in 1987A, so this was a bit long ago compared to 2023. But what's historic about it is that it's the closest supernova that occurred in the era of telescopes. And it's pretty cool. This one went off in the Large Magellanic Cloud. You all remember seeing that a bit earlier? The light from this one took about 160,000 years to reach us. At that time, we were Homo sapiens already, living in caves, learning how to make tools, sitting with our companions around. It took 160,000 light years for that to reach us finally in 1987. So what we're seeing here in this many images put together is after the supernova went off, there was a shock wave, and then it's hitting the debris that was released around that supernova way before, when the star was still a star. And that collision is leading to several of these hotspots. Oh, let's see if this is working. It doesn't work again, but yes, the collisions led to several hotspots around. This is something we can actually actively image. We saw this with the Hubble Space Telescope all over from 1994 to 2017 or so, that beautiful hotspot image. All right, so we talked about, please come in, that's okay. You can sit over here. So we spoke about massive stars and explosions and debris and stuff being ripped apart and everything. But is it necessarily true that all of the star actually gets ripped apart? Or does it leave something behind? Well, just like us, there are corpses of stars as well. And these are, in fact, eternal corpses. And these corpses are black holes and neutron stars. Let's take the first one. This is a neutron star, or in fact, this is more accurately a pulsar. Now, a neutron star is so dense, right? The neutrons are packed so tightly together that a small teaspoon of this thing, a single teaspoon of a neutron star, will weigh as much as Mount Everest. That's how dense this is. It is the most dense object you can find in our universe. And occasionally they become these cosmic lighthouses, these pulsars, because of their intense magnetic fields that cause particles to accelerate really fast and send out these jets or beams of light in our direction every now and then. They're super cool. They're really, really extremely well calibrated as well. Now, those are about 1.4 to 2 times the mass of the sun. It's not so heavy, but very, very packed, so it's dense. Let's come to our of the sun, from 2 to 80 times the mass of the sun. Now, these guys are formed amongst the most massive stars, and they are famous because of their quintessential gravitational field, a field so strong that not even a ray of light can escape once it enters. So what's the hope for us, right, if we go into a black hole? Speed of light is the fastest speed for any entity in our universe. So now we saw what happens when a massive star dies. What happens when you have a binary star system that decides to go towards their final end. So one star goes supernova, leaves behind the other star. One of two things can happen in this case. Either the stars are orbiting, one star goes supernova, the binary is disrupted, and the two go in either direction. You have a black hole in one direction and the other star in another direction. But let's say the explosion was not so powerful. What happens otherwise? The binary will still stay intact. Something is going around each other now, but instead of a star, you're going to have a black hole going around a star. So it's not just two stars going around each other. You can have a black hole plus a star going around each other now. And in fact, the very first black hole that we confirmed in existence was in fact a member of such a binary system. This is Cygnus X1. It's in the constellation of Cygnus. It's the constellation of the Swan, also very visible from our northern hemisphere. And here, instead of having a vampire star, they are going to have a vampire black hole, aka vampire zombies. All right, now you have a vampire zombie which has a star and a black hole. What's left? Well, two black holes, right? Let's say that the other star also explodes, the binary remains intact, so now you have two corpses going around each other. That is these two black holes. These two black holes are very special, very, very special in the history of not only astronomy, I would go so far as to say even for mankind as well. Because for the first time, we found something celestial without using telescopes. These two black holes are the first ones to tell us the existence of gravitational waves. Two black holes here going around each other. Each one weighs 30 times the mass of the sun. So the total mass of the newly formed black hole at the end, when they finish their cosmic dance, is 60 times the mass of the sun. And why are they so cool? Do you all see this thing going around? Those are the gravitational waves. The motion of the two black holes causes ripples in the very fabric of space and time itself. Imagine that. You don't need a medium anymore. You can create waves just by getting two black holes to go around each other. And this is also true for two neutron stars that go around each other too. We've found plenty of such systems as well. Now, how did we find these gravitational waves? These guys don't emit light, right? They're black holes, right? There's no star around them. So how do you find it? Well, we don't actually try to see them. We try to hear them. Was that audible? Let's try again. Was that audible? Okay. Welcome to the era of gravitational wave astronomy. No longer do we need only telescopes. Astronomers are not those people who just sit around in nice observatories, sitting behind the lens of massive telescopes. We can now do this just with the ripples in the fabric of space-time. So this is LIGO. LIGO stands for Laser Interferometer Gravitational Wave Observatory. And unlike telescopes, which are perched over great mountains or big deserts, right? These guys are built in underground tunnels underneath two observatories here. Each of them goes to about 4 kilometers long. That's how long the tunnel is. Do you all see that? It's an L-shaped tunnel like this. And there's one in Livingston, which is in Louisiana, and Hanford, which is in Washington. So what does happen inside these new age observatories? Again, remember, these are not telescopes. These are all operating underground. Well, this is an amazing feat of engineering. So you have your two black holes doing the cosmic tango, going around each other. At one point, they send out gravitational waves, two lasers going back and forth between the mirrors, keep moving until the final coalescence of the black hole itself. So that movement, if we watch it again, that movement of the laser, mimics the pattern of the gravitational waves, because those gravitational waves go out from the black hole, come all the way to Earth, and also make those laser beams go back and forth. The mirrors at the two ends are what give you the pattern. And do you know how much the mirrors move? Just about a proton's diameter. That's how tiny the fluctuations are, and we have engineered it. It's quite a feat of engineering, not just an astronomical feat, but also an engineering feat. And this is why three individuals, in fact, won the Nobel Prize in 2017. Ray Weiss left us sadly a few months ago, but the others are still with us. And of course, everybody knows Kip Thorne, who is the scientific writer behind the acclaimed Interstellar. I mean, clearly, right, he's an expert. So Nolan didn't, cheap anything. Okay, so what exactly happened here? A few billion light years away, two galaxies played their cosmic tango, right? They went around each other, the gravitational waves now traveled all those billion light years. Finally, that movement created a signal. The chirp. No longer do we have to wait to see anything. We can now begin to hear our universe as well. All right, so what is our stance right now? Where led era, it is going to be an era of data revolution. A colossal data flood literally awaits us at our doorstep. This is LIGO's haul. LIGO has been finding over 200 2025. And what you see here is, in fact, all the different types of black holes and neutron stars and the masses of those objects as well. This is the currently largest optical telescope on our planet. This is called the Gran Telescope de Canarias. It is in the Canary Islands. It's in La Palma. I worked here for a couple of years. Beautiful place. One of the great things about being an astronomer is that you actually get good reason to go up on a mountain and just be there for some time. Beautiful locations to travel to. This is currently the largest telescope we have. Now, this is another interesting telescope that just got operational a few months ago. This is called the Vera Rubin survey. LSST is just a way of saying it's a transient survey. So this is what we are using right now to accumulate data on all sorts of supernovae and mergers of all sorts of things. So this is a very, very important advancement for us in astronomy. Earlier, we used to capture maybe 3 or 4 supernovae a night. With Vera Rubin, we're going to get about 1,000 supernovae a night. Not to mention, over a decade, it's going to find millions to billions of binary stars as well. So it's a huge deal for our field. And coming now to the space telescopes, everyone's favorite these days is the Webb Space Telescope. This is NASA's very own. It is a successor of the Hubble Space Telescope, which has been going strong since 1990, which is really great. But while Hubble can explore the nearby galaxies, we can go back in time with James Webb, going back to, in fact, the very first galaxies of our cosmos from 13.5 billion years ago. That's just about 500 million years after the Big Bang. Coming soon. What's next then? Well, this is the largest proposed telescope that's confirmed it's going to happen. This is called the Extremely Large Telescope. Thank you. That's a very creative way astronomers name things. Funded by the EU in Chile. It is going to be amazing because it will capture more than 10 times, up to 15 times more light than the largest current telescope that we have on Earth. And how is that going to benefit massive stars? Because we can now go beyond just the Magellanic Clouds, the Milky Way, to much more distant realms of our universe and collect high resolution, high precise data of massive stars and understand further the question about the origin of life. Next is the Einstein telescope, which is a gravitational wave observatory. It's projected for 2030. I think I forgot to mention this. This is projected for 2030. Einstein is proposed for 2035, but they're still trying to figure out at least 10 kilometers long each tunnel. So I'm not sure where they're constructing it, but it is an EU-funded mission. And beyond finding black holes, it's going to go into more fundamental questions like understanding the nature of dark matter, what happened in the first moments after the Big Bang, early universe cosmology, and also possibly cosmic strings. Although we don't know how that might go, it's a possibility. And the Nancy Grace Space Roman Telescope. This one is the next generation after James Webb, and it was slated for release in 2027. Beyond our LSST survey, it was going to cover a lot of our sky, right? And make a big coverage of all sorts of transient supernovae and black hole binaries. However, this morning, ta-da, I saw this. So it appears that this might be canned. And we were so close to finishing everything and launching it. We don't know. We'll find out. Let's hope that's it's not as bad as it looks, but this is the official NASA website release. There was nothing else updated for a while now, so who knows? And unfortunately, same story also for LIGO. A $9 billion federal funding cut proposed by the current administration means we will have to let go of one of LIGO's instruments. What that means is that all you can say is, hey, two black holes merged, but we don't know where. We need at least 2 detectors to triangulate and find the source. So without one of them, all we can say is something happened, but we don't know where. Anyway, I don't want to end on this note. This is an outreach talk. So if there are people here, and especially the youngsters who are going to be policymakers, lawyers, politicians, please take our cause and do take it forward. Even if you don't wish to work in science, I hope you can contribute towards advancing our human civilization beyond just the material concerns and keep pushing us forward. It's also in the way we think. And for the budding astronomers in the audience, well, despite the momentary bleakness and darkness, the future is here. If you were ever considering to become an astronomer, now is the time to really look up at the stars and wonder what they are. Thank you very much.
All right. We will now take questions. You are welcome to ask them out loud, but if you are nervous, you can also type them into this Google form by going to the link or by scanning the QR code. I'll be looking at the form, so taking a mix of in-audience questions and online questions. So we'll start with you. So the question was, why are contact binaries rare?
Great question, and you really were observing. I could see that. I felt that energy. I'm a teacher, so I noticed all the students were paying rapt attention. That goes to all you boys at the back, huh? Anyway, thanks for the question. So why are contact binaries rare? Because they are very short orbital period systems. So in general, nature likes to form them very rare. They are just born rare to start with. So you don't get a lot of close systems to start with. Most of them are a little bit further apart. And think of this as well. if they're already so close, a lot of them may have ended up merging before they became stars too. So this is why they are rare to start with, of course. Okay. Great question again.
So what determines for a massive star if they have a supernova and if they become a neutron star or a black hole?
Great. So what makes these decisions, right? So it is initially the mass itself. And secondly, it's also what we call the metallicity of the star. It just tells you what's the chemical composition of the star to start with. That's a secondary effect. So the more massive you are, the more likely you are to collapse to a black hole. And if you're really massive, like over 100 times the mass of the sun, sometimes you may not even explode before collapsing. You just collapse all the way straight, skipping the supernova stage as well. But those are super rare. They're the rarest forms of stars. Does that answer your question?
And I'll do one online. So I think we have a question about one of the transient curves you showed. So what does the data moving up and down on the graphs showcase? What are you actually measuring there?
I'll have to remember which one that.
With the eclipsing binaries showing the eclipse, yeah.
Should I go back to that? Maybe I can just explain it.
Yeah, either way.
So the question is about those eclipsing binaries, right? What did the graph represent? It just shows us the brightness. Maybe I should talk to the camera. Okay, it just shows us, is one over there. It shows us the brightness of the star. So the brightness dims or goes up depending on when the eclipses occur, right? So if there is no eclipse and the two stars are just facing us, it's a flat line. But the moment one covers the other, you have a dip in the brightness. And that's what the curve.
When you say mass of the star, you're dealing with the size of the star?
No,
So
how
what
heavy,
is meant by mass of the star?
how heavy the star is.
How do you determine?
That's
And
a
how
great
do you
question.
determine that?
Great question. So there are many ways to do that. By looking at the curves, the transient curves, we can use mathematics to create models and then determine it from the curves. You can also determine it based on the brightness of the star as well and how hot it is. We do this all the time as well. You put these on evolutionary diagrams and then indirectly infer the mass of the star.
All right, I'll do another online one. What happens inside a black hole?
Oh, it had to be that. What happened inside the black hole is for people who have gone inside a black hole and come out to tell us the story. Unfortunately, we really don't know what happens inside a black hole. Information gets destroyed. Now, a lot of beautiful science fiction comes out from things that go inside a black hole. There are these mathematical constructs called wormholes. Some of you might have heard of that. That's supposed to be like a little tunnel connecting one black hole and another. And you can maybe get completely ripped apart in one and then emerge out the other like nothing happened. So we don't know is the answer.
Right, question right in the front.
Ooh.
What are evolutionary diagrams?
What are evolutionary diagrams? Okay, so like us, stars have a life cycle, right? So they're born and then they grow old. And then we can track them as they move through a certain diagram as they grow older. They change in brightness, they change in how hot they are on the surface. And by tracking that movement, we can know the age of the star. Great question. Thank you.
What problem are you working on right now that you are stumped by?
The
Pick
truth.
one.
The truth, funding. Funding for future projects. That is probably the problem I'm stumped by because I don't know how I can solve that by myself. Scientifically, we are making some progress on the kind of supernovae that come from these kind of merger-born stars that are born from mergers, and we're trying to explore that variety of supernovae that come from them because it's still an open question. We don't know how such stars end up exploding. So that's an open avenue. I'm not sure I'm completely stumped by anything there. We're just starting off, but the funding is a big problem. Mm-hmm.
So I guess all the different binary system that you described. I forget the name of it. There was one case of, I think it was a planet was detected around basically in its current form, it's orbiting like I think it's like a pulsar and the white.
Oh, yes.
dwarf. But any of these, I guess any of these like systems where kind of rather be formed as a binary system. I guess, are there any ones that you've been studying that result from, I guess, interaction or something like
Right.
one star captured by it?
Yeah. So question about a binary system that you're observing, how, like, what are the properties of the system?
And something about a planet in there too.
Yes.
Yeah, no, sorry, that was just one example I remember reading about like years ago.
Okay.
So just kind of anything similar to that kind of.
At the moment, I'm actually set to observe those contact binaries because there aren't a lot of them and there's a small sample to begin with. So we're going to work on a telescope, sit behind a telescope, me for the first time. I'll know what it means to have sleepless nights because I never did observing before. So that's my next project, to look at my own contact binaries. No, not a problem.
Question?
I'm just wondering, what else can you listen to? Saying you're moving to rather than viewing, listening to, what else are you picking up? Or what else are you targeting?
Oh, it's a
So
good
what
question.
else can astronomers listen for?
Very good question. So this particular field is right now, gravitational waves is the only way we have dubbed a signal. So I'm using the word dubbed because it's actually a visual signal. And now we've given it an audio form, right? So if anything has a signal, you can make an audio form out of it. This just happens to be at a frequency that we can actually hear for humans. So it would still be gravitational waves.
Okay, I'll do one online. Can you, oh, I just lost the question. Can merging binary neutron stars accumulate enough mass to form a black hole?
Oh, what a question. Okay, my answer is probably not. It will just make a more massive neutron star. But those end up also exploding, as we have seen. One of those also created a beautiful electromagnetic transient. This means something with light that came out. So two neutron stars went around each other. They merged. Now, unlike a black hole where nothing happened afterwards, this one released some extra light. And in fact, we think in such neutron stars is where we make very rare elements like gold and platinum, for example, which we didn't know before.
Okay, question?
One of the,
So,
yes.
so what about that 7-star system? You talked about binary stars and how one exploding or sucking mass can affect the other, but what about for a 7-star system? Does one star exploding affect the others?
Great question. Yes, if the star can explode, which is not a given, for example, the sun is not going to explode. It's going to live a very calm life and die off. But if a massive star exists in that system, and if it explodes, it can disrupt the family of stars. By disrupt, I mean right now everyone's going nicely around. This can just boom, cause all of them to go haywire here and there. Or maybe one of them can explode and then collapse into a black hole without disrupting the system as well. So it depends totally on the initial mass of the star.
You had a question. Do binary stars have a similar composition, or is there any kind of other pattern you see in the composition?
By composition, do you mean the chemistry of the star? So that again depends on the environment in which they're found. So if they're found in our neighborhood, right, then they will have the same composition as the sun. But if they're found in more distant galaxies, it would have a more primordial composition, much more earlier from our universe's time. So it totally depends on where they are when you observe them.
Okay, I'll do another one from online. Keep saying that and then I miss it. All right. How do black holes, vampire zombies, or vampire stars affect interactions between galaxies?
Well, they're too small to affect the interactions between galaxies. So galaxies are a few billion times the mass of the sun. A black hole is comparatively not so massive. It's about 2 to 80 times the mass of the sun. So by itself, those vampires are not going to hurt galaxies, just other stars. Oh, okay, that brought new questions.
So are the stars that are farther away the oldest ones?
Okay, so the further you look back, right, in fact, the younger the stars are, right? Because you're looking at them as they were some billion years ago, right? Because the time for light to travel from them has taken that long. So that's why we say the further back you look, the earlier back in time you're looking as well. Does that answer the question? Okay, of course.
Okay, I think we'll end with one online. What got you interested in astronomy?
I love this question. Okay, what got me interested in astronomy? Well, like any other kid, I loved stars, and I thought they're the best things to study. And I always felt very drawn to the fact that just being here on Earth, you know, using the laws of physics that work here to drive a car or to boil an egg, it's the same things that goes on in them as well. And we as humans have advanced so much that we've gone beyond just thinking about ourselves and, you know, our bodies and our whatever is just around us. Everything that works here on planet Earth works elsewhere as well. And that really struck a chord with me philosophically as well. And I just enjoyed the fact that stars are so nice to look at. Look at all the pictures.
All right, if you'll advance one slide. Now I know this is the reason you all are actually here, is for the chance to win some astronomy merch, not listen to me ramble trivia questions at you. So how this works is each seat has a number on it. Usually this is to sign the seats to take a horrible physics exam.